Hey guys, tonight we're going to explore something almost too old to comprehend. Light. Ancient light. Light that has been traveling for nearly 14 billion years, quietly drifting through the expanding darkness, patient beyond imagination, just to reach you, here, in this moment. Not starlight, not sunlight, something far older than both. This is the oldest light in the entire universe, a faint, cold glow that surrounds you right now, invisible but everywhere, filling every corner of space with a whisper from the very beginning of time itself. This light began its journey before stars existed, before galaxies formed, before there was anything you would recognize as the universe. It was released when the cosmos was still a glowing fog, hot, dense, and blinding, and it has been quietly falling toward you ever since. Patient, cold, impossibly ancient. By the end of this journey, you'll understand what this primordial light is, how we discovered it completely by accident, and what message it has been carrying across billions of years, a message from a universe that no longer exists. Before we go any further, if you enjoy this kind of calm cosmic wandering, a like or subscribe genuinely helps the channel grow. But only if you actually enjoy this. No pressure at all. Just a small thing that makes a real difference for me. Now, dim the lights if you haven't already. Turn on a fan if the white noise helps. Get comfortable. Let your breathing slow. Let your thoughts settle like dust drifting in still air. And let me ask you something quiet. Have you ever wondered what the universe looked like before there were any stars to illuminate it? Before light could travel freely through space? What did existence even look like when the cosmos was so hot and dense that photons couldn't escape? Trapped in an endless fog of energy? And when light was finally released, when the universe cooled just enough to become transparent for the first time, where did that light go? Did it simply vanish? Or is it still out there, somewhere, still traveling through the darkness? Could you, right now, in this very room, still catch a faint glimpse of the universe's very first moment of clarity? What would that ancient glow feel like if you could somehow sense it, not with your eyes, but with something quieter, something more patient? And slowly, something shifts. The room around you begins to feel less solid. The walls, the ceiling, the familiar boundaries of your space, they seem to thin, to become transparent in a way that isn't alarming, just different. You're not leaving your body. You're not traveling anywhere. You're simply becoming aware of something that was always there, a faint glow, everywhere, in every direction. Not bright enough to see, but present enough to sense. It has been here all along, filling the space between atoms, drifting through walls, passing silently through everything you've ever known. This is the oldest light in the universe, and it has been waiting patiently for you to notice it for nearly 14 billion years. Now, let's drift into its story. In 1964, two radio astronomers in New Jersey were trying to make their antenna work properly. Their names were Arno Penzias and Robert Wilson, and they were not searching for the secrets of the universe. They were engineers, practical men. They had been assigned to work with a large horn-shaped antenna at Bell Labs in Holmdel, New Jersey, and their job was straightforward: calibrate the instrument, eliminate interference, make it useful for satellite communications. But there was a problem. A persistent hiss. A low, steady noise that wouldn't disappear no matter what they tried. It was there in the morning, It was there at night. It was there when they pointed the antenna at New York City. It was there when they pointed it at the empty sky. It seemed to come from everywhere at once, with a maddening uniformity that made no sense. They checked the wiring. They recalibrated the electronics. They examined every component, every connection, every possible source of interference. Nothing worked. The hiss remained. Then they noticed something else. Pigeons had been nesting inside the horn of the antenna. Perhaps, they reasoned, the droppings were somehow causing the noise. It sounded absurd, but at this point, they were willing to try anything. So they climbed inside the antenna, cleaned it out thoroughly, and relocated the pigeons to a facility far away. The pigeons found their way back. They were removed again. And still, the hiss continued. Months passed. The mystery deepened. The noise was not coming from the equipment. It was not coming from the ground. It was not coming from any known source on Earth or in the sky. It was simply everywhere, constant, unchanging, as if the entire universe were quietly humming at a single, faint frequency. What Penzias and Wilson didn't realize, what they couldn't have known at the time, was that they were listening to the oldest sound in existence. Not a malfunction, not interference. They were detecting the faint afterglow of the Big Bang itself, stretched and cooled across nearly 14 billion years, still filling every corner of the cosmos with its ancient whisper. They had accidentally discovered the cosmic microwave background, and nothing in cosmology would ever be the same. Now, let's drift a little further back, much further, to a time before this light was released, to a universe you would not recognize at all. Go back far enough in time, and the universe wasn't dark. It was blinding. Not with starlight, because stars didn't exist yet. Not with any familiar source of illumination. Blinding with raw primordial heat. A universe so hot and so dense that light itself was trapped, unable to travel more than a fraction of a millimeter before scattering off the seething plasma that filled all of space. Imagine it. You are floating in this ancient cosmos. There is no up or down, no landmarks, no reference points. Just heat, just light, just an infinite fog of energy so intense that visibility is effectively zero. If you could somehow survive here, which you absolutely could not, you would see nothing but glowing brightness in every direction. Not empty brightness, heavy brightness. Brightness with weight. Brightness that presses against you from all sides. The temperature is millions of degrees. Then, as time passes and the universe expands, it cools to hundreds of thousands of degrees. Still impossibly hot. Still opaque. Photons, particles of light, are constantly being absorbed and re-emitted by the free electrons and protons that fill space. Light cannot escape. It cannot travel. The universe is a wall of energy, and there is nothing to see because seeing requires light to reach your eyes, and light cannot move freely here. This is not emptiness. This is the opposite of emptiness. This is a universe so full, so saturated with energy, that existence itself is a blinding, formless glow. And this state persisted for hundreds of thousands of years, not days, not weeks. Hundreds of thousands of years of cosmic opacity as the universe slowly, patiently cooled. Slowly, we drift forward in time. The universe is expanding, cooling, and something is about to change. About 380,000 years after the Big Bang, something quiet but extraordinary happened. The universe had been expanding and cooling steadily, and it finally reached a temperature of about 3,000 Kelvin. Still hot enough to melt any metal you've ever heard of, but cool enough for something remarkable to occur. For the first time, electrons could settle down. Before this moment, electrons were too energetic, too wild, too hot to bind to atomic nuclei. They flew freely through space, scattering photons in every direction, keeping the universe opaque. But now, finally, the temperature was low enough for electrons to be captured by hydrogen and helium nuclei. They settled into orbits. They became bound. And suddenly, there was nothing left for photons to scatter off. Light was free. For the first time in the history of the universe, photons could travel without being immediately absorbed or deflected. The cosmic fog lifted. The blinding opacity that had filled all of space suddenly became transparent. Light, which had been trapped for 380,000 years, was released in a single cosmic moment, a flash of radiation that filled the entire universe simultaneously. This moment has a name: recombination. Not because things were combining again, they had never been combined before, but because electrons and nuclei were uniting for the first time into neutral atoms. It's a bit of a misnomer, really. A quirk of scientific naming. But the event itself was profound beyond measure. The universe, after nearly 400,000 years of glowing opacity, became see-through, and the light released that day began its long, quiet journey through the expanding darkness. That light did not stop. It had nowhere else to go. So it just kept moving, drifting through the expanding emptiness, through the void that was growing larger with every passing moment, through the cosmic dark ages before any stars had formed. Think about that for a moment. Light, traveling through absolute darkness. No destinations, no sources. Just ancient photons moving through space that was stretching as they moved. Their wavelengths growing longer. Their energy slowly fading. Their journey measured not in miles, but in billions of years. This light witnessed the slow birth of the first structures. It passed through regions where gravity was beginning to pull hydrogen into denser clumps. It drifted past the formation of the first stars, massive, brilliant, short-lived giants that would not ignite for hundreds of millions of years. It continued through the assembly of the first galaxies, the first galaxy clusters, the vast cosmic web of filaments and voids that would become the architecture of the universe. And it never stopped. That same light is still falling through space right now. Some of it is passing through your room at this very moment. Not metaphorically, literally. Ancient photons, born in the fire of the early universe, are drifting through your walls, through your furniture, through your body as you listen to these words. You can't see them. Your eyes are not sensitive to their wavelength anymore. But they are there. They have always been there, patient, ancient, and completely indifferent to whether anyone notices them or not. Now let's talk about why this light became so quiet. When this light was first released, it was hot, intensely hot, glowing at about 3,000 Kelvin. It would have appeared as a deep orange-red color, visible to any eye that might have existed to see it. If you had been there, the entire sky would have been a uniform, glowing ember in every direction, beautiful in its way, and blinding. But the universe has been expanding ever since, and as space stretches, light stretches with it. This is not intuitive. We don't experience it in daily life. But light is a wave, and when the medium it travels through expands, the wavelength of that light expands too. Longer wavelengths mean lower energy. Lower energy means cooler temperatures. And over nearly 14 billion years of cosmic expansion, that hot orange glow has been stretched into something far, far colder. The wavelength grew longer. The color shifted from visible light to infrared, and then beyond infrared into something even colder, microwave radiation. What was once a blinding glow is now a faint whisper, stretched thin across billions of years, invisible to human eyes, detectable only with the right instruments. It's a bit like a song playing on a record that's slowly, slowly winding down. The pitch drops. The tempo stretches. What was once vibrant becomes muted. Except this record has been winding down for nearly 14 billion years, and the song has stretched from a brilliant chord into a nearly inaudible hum. Today, the cosmic microwave background has a temperature of about 2.7 Kelvin. That's 2.7 degrees above absolute zero, the coldest temperature possible, the point at which all molecular motion stops completely. Let that sink in for a moment. This ancient light, which began its journey as a searing glow hot enough to melt anything, has cooled to a temperature colder than any place on Earth has ever been. Colder than the dark side of the moon. Colder than the permanently shadowed craters at the lunar poles, which never see sunlight and never warm above about 30 Kelvin. This light is colder than all of that. This is the ambient temperature of the universe itself. If you were floating in deep space, far from any star or galaxy, shielded from all sources of heat, this is the temperature you would eventually reach. 2.7 Kelvin, the residual warmth of creation, diluted by nearly 14 billion years of expansion. This is what almost nothing feels like, a chill that has no source and no end. A background hum so faint that it took incredibly sensitive instruments to detect, and so pervasive that it fills every cubic centimeter of the observable universe. If you could somehow tune your senses to detect microwaves instead of visible light, you would notice something strange, something that would fundamentally change how you perceive existence. The entire sky hums, not from one direction, not from one source, not from any single point you could locate or identify, from everywhere. The cosmic microwave background fills every corner of space with a faint, almost imperceptible glow. There is no spot in the observable universe where it doesn't exist. There is no direction you could look where it would be absent. This is not a signal from a distant object. This is not radiation from a star or a galaxy or any source you could point to. This is the background radiation of reality itself, the leftover warmth of a universe that was once too hot to see, now stretched and cooled into an omnipresent whisper. You are bathed in it right now. About 400 photons from the cosmic microwave background occupy every cubic centimeter of space around you. They are passing through you as you listen to this, through your walls, through the earth beneath you, through everything. They carry almost no energy now. Their warmth has been stretched to almost nothing, but they are there, everywhere, always. It's humbling in a quiet way to realize that the oldest light in the universe has been silently surrounding you for your entire life, filling the space between atoms, drifting through every room you've ever entered, and you never knew. It was too faint to notice, too cold to feel. But it was always there, a constant companion, a silent witness to every moment of your existence. Let's return, for a moment, to those two frustrated engineers in New Jersey. Arno Penzias and Robert Wilson were not looking for the edge of the universe. They were not cosmologists. They were not theorists dreaming of the Big Bang. They were practical men with a practical problem. Their antenna wouldn't stop hissing. The horn-shaped antenna at Bell Labs had been built for satellite communications, and Penzias and Wilson had been assigned to make it work. But no matter what they did, a persistent, uniform noise remained, a background hiss that seemed to come from every direction equally. It wasn't strong, but it was constant, and it was driving them slightly mad. They spent months troubleshooting. They checked for interference from nearby cities. They examined the electronics for faults. They pointed the antenna at different parts of the sky, at different times of day, in different seasons. The hiss remained unchanged. It didn't vary with direction. It didn't vary with time. It was simply there. And then there were the pigeons. Pigeons had made a nest inside the horn of the antenna, and they had left behind what Penzias and Wilson delicately referred to as a white dielectric material. In less scientific terms, bird droppings. Perhaps, they reasoned, this was somehow causing the noise. They climbed inside the antenna, carefully removed the pigeons, cleaned out everything they had left behind, and sent the birds to a facility miles away. The pigeons came back. They were trapped and removed again. And still, the hiss continued. It was only when Penzias happened to mention the mystery to a colleague who happened to know about theoretical work being done at nearby Princeton University that the pieces finally fell into place. A group of physicists at Princeton, led by Robert Dicke, had predicted that if the Big Bang had actually happened, there should be residual radiation left over. A faint afterglow, stretched and cooled, filling all of space. They were actually building an instrument to look for it. Penzias and Wilson had found it first, by accident, while cleaning up pigeon droppings. They published their discovery in 1965 in a paper so understated that it barely hinted at the cosmic significance of what they had found. And in 1978, they shared the Nobel Prize in Physics for accidentally discovering the echo of creation. The cosmic microwave background is not just old light, it is a photograph. Think about that for a moment. When you take a picture, you capture light that was reflected off objects at a particular moment in time. The image freezes that moment. It preserves it. And when you look at the photograph later, you are seeing the past. Light that was captured and stored, representing a moment that no longer exists. The cosmic microwave background is exactly the same thing, except on a cosmic scale. It is a snapshot of the universe when it was only 380,000 years old, an infant cosmos captured in wavelengths that have been traveling ever since. In that image, frozen in faint radiation, we can see the seeds of everything that would come later, the tiny density fluctuations that would eventually collapse under gravity. The slight variations in temperature that mapped out where galaxies would form, the first hints of the cosmic web that would become the large-scale structure of the universe. This is the earliest picture we will ever have. Before this moment, the universe was opaque. Light could not travel freely, so there is nothing older we can see. The cosmic microwave background marks the boundary of the visible past. Beyond it lies the epoch of opacity, and beyond that, the Big Bang itself. Events we can calculate and model, but events we can never directly observe with light. This is our baby picture of everything, and we almost threw it away as antenna noise. The CMB is almost perfectly uniform. When you measure its temperature across the sky, you find that it is the same in every direction to an extraordinary degree of precision. This uniformity was one of the strongest early confirmations that the Big Bang theory was correct. It showed that the early universe was remarkably smooth and homogeneous, just as the theory predicted. but it's not perfectly uniform. Not quite. If you measure carefully enough, and scientists have measured very, very carefully, you'll find tiny temperature variations, fluctuations of about 1 part in 100,000. If the average temperature is 2.725 Kelvin, these fluctuations are measured in millionths of a degree, barely perceptible, almost nothing. But these tiny differences are not random noise. They are echoes of something profound. These fluctuations are the frozen remnants of quantum variations from the earliest moments of the universe, stretched to cosmic scales by the expansion of space. In the first fraction of a second after the Big Bang, tiny quantum uncertainties, fluctuations in the density of energy on the smallest possible scales, were blown up to enormous sizes by a process called inflation. They became the seeds of all structure in the universe. The slightly denser regions in the primordial plasma had slightly stronger gravity. They attracted more matter. Over hundreds of millions of years, they collapsed inward, forming the first stars, the first galaxies, and eventually, everything you've ever known. The patterns you see in the cosmic microwave background are the original blueprint of cosmic structure, the map that determined where galaxies would form and where voids would remain empty. Those tiny bumps became everything, including you. In 1989, NASA launched a satellite called the Cosmic Background Explorer, COBE. Its mission was to map the cosmic microwave background with precision no ground-based telescope could achieve. From Earth, the atmosphere interferes, water vapor absorbs microwave radiation, mountains and buildings create shadows. To truly see the ancient light, you need to get above it all. COBE did exactly that. Orbiting high above the atmosphere, it scanned the entire sky, measuring the temperature of the CMB with unprecedented accuracy. And what it found confirmed everything cosmologists had hoped and revealed something they hadn't expected. First, COBE confirmed that the CMB was an almost perfect blackbody spectrum. This is a technical term that essentially means the radiation matches exactly what theory predicted. The signature of a hot, dense, early universe that has been cooling and expanding for billions of years. The match was so precise that it became one of the strongest pieces of evidence for the Big Bang theory. But COBE also found the ripples. For the first time, scientists could see the tiny temperature variations, the 1 part in 100,000 fluctuations that marked the seeds of cosmic structure. The CMB was not perfectly smooth. It had texture, and that texture matched what was needed for galaxies to form. George Smoot, the lead scientist on the COBE project, held a press conference to announce the results. When asked what it was like to see the data, he said something that made headlines around the world. "It's like looking at the face of God." Whether you take that literally or poetically, the sentiment was clear. For the first time, humanity had directly observed the infant universe, the conditions that gave rise to everything we know. It was a profound moment in the history of science, and it was just the beginning. A decade after COBE, NASA launched an even more sophisticated instrument, the Wilkinson Microwave Anisotropy Probe, or WMAP. Its mission was to look closer, to sharpen the image, to extract every bit of information hidden in the ancient light. Where COBE had shown that the ripples existed, WMAP measured them with far greater resolution. It mapped the tiny temperature variations across the entire sky with such precision that cosmologists could analyze not just the presence of fluctuations, but their specific sizes, shapes, and patterns. And from this data, something remarkable emerged: the fundamental parameters of the universe. By analyzing the patterns in the CMB, the way temperature varied on different angular scales, scientists could calculate the geometry of space itself. They could determine whether the universe was curved like a sphere, saddle-shaped like a hyperbolic surface, or flat like an infinite plane. The answer came back clearly. The universe is flat, or very close to it. WMAP also allowed scientists to measure the age of the universe with unprecedented precision. 13.77 billion years, plus or minus about 60 million years. This wasn't a guess or an estimate based on indirect methods. It came directly from the ancient light, from patterns that had been frozen in place when the universe was less than 400,000 years old. Perhaps most remarkably, WMAP revealed the composition of the cosmos. By analyzing the CMB, scientists determined that ordinary matter, the stuff that makes up stars, planets, and human beings, accounts for only about 5% of the universe's total content. About 27% is dark matter, a mysterious substance that interacts gravitationally but doesn't emit or absorb light. And the remaining 68% is dark energy, an even more mysterious force that is causing the expansion of the universe to accelerate. All of this hidden in the faint glow of ancient light. A cosmic census written in microwaves. In 2009, the European Space Agency launched the Planck satellite, pushing the resolution even further. Planck was designed to be the ultimate CMB observer, the sharpest eye humanity has ever turned toward the oldest light. And it delivered. Planck mapped the cosmic microwave background with such extraordinary precision that cosmologists could identify features they had only theorized about before. Acoustic oscillations, ancient sound waves frozen into the fabric of the early universe, became clearly visible for the first time. These were not metaphorical sound waves. They were real pressure waves, rippling through the hot plasma before recombination, compressing and expanding the primordial matter in rhythmic pulses. When the universe became transparent and light was released, those waves stopped. They froze in place, and their patterns were preserved in the CMB, like ripples frozen in ice. Planck could see them. Planck could measure them. And from those measurements, cosmologists refined their understanding of everything. The age of the universe was updated to 13.8 billion years. The proportions of matter, and dark energy were calculated with even greater precision. The geometry of space was confirmed to be flat, and the patterns in the CMB were found to match the predictions of inflation, a theory that describes the first fraction of a second after the Big Bang, when the universe expanded faster than light. The oldest light in existence had become a precision instrument, a cosmic measuring tape, a message from the beginning of time, revealing the universe's deepest secrets to anyone patient enough to decode it. After recombination, after the light was released, and the universe became transparent, something unexpected happened. Nothing. The CMB had been emitted. The cosmic fog had lifted, but there was nothing else to see. Stars had not yet formed. Galaxies did not exist. The universe was filled with hydrogen and helium gas, slowly cooling in the expanding darkness, but there were no sources of light, no illumination, just emptiness and silence. Astronomers call this period the cosmic dark ages. It lasted for hundreds of millions of years, a span of time longer than complex life has existed on Earth, longer than the dinosaurs ruled, longer than almost anything we can intuitively grasp. And during all of that time, the universe was dark. Not the darkness of a cloudy night, where light exists but is hidden. True darkness. the absence of any light sources whatsoever. The CMB was still there, fading into the microwave range, but there was nothing else. No stars to twinkle, no galaxies to glow, just cooling gas, expanding space, and infinite patience. Gravity was working, of course. Slowly, inexorably, the denser regions of gas were beginning to contract. The seeds that would become stars and galaxies were already present in the tiny fluctuations of the CMB, but the process was slow, agonizingly slow. Hundreds of millions of years of quiet collapse with nothing to show for it. And then, eventually, something changed. Party 2. Eventually, gravity won. Dense pockets of hydrogen collapsed inward, pulled together by their own weight, compressed by forces that had been building since the first fluctuations in the primordial plasma. As the gas compressed, it heated. As it heated, it compressed further. A runaway process began, a cascade of increasing density and temperature that could only end one way. Nuclear fusion ignited. The first stars were born. Astronomers call these ancient giants population 3 stars, and they were unlike anything that exists today. They were massive, perhaps hundreds of times the mass of our sun, because the gas they formed from contained no heavy elements, no carbon, no oxygen, no iron, just hydrogen and helium, pure and primordial. Without heavy elements to help the gas cool and fragment, only the most massive clumps could collapse quickly enough to form stars. These first stars burned hot and fast. Their surfaces blazed at temperatures far higher than our sun, glowing blue-white with incredible intensity. For the first time in hundreds of millions of years, there was light in the universe. Real light. New light. Not the fading echo of the Big Bang, but fresh photons generated by nuclear fires in stellar cores. The cosmic dark ages ended. But these first stars were short-lived. Massive stars burned through their fuel quickly, and within a few million years, they began to die. When they died spectacularly, exploding as supernovae, blasting their outer layers into space, seeding the universe with the first heavy elements: carbon, oxygen, iron, gold. All the elements heavier than helium were forged in these stellar furnaces and scattered across the cosmos when the stars exploded. Without those first stars, without their brief and violent lives, planets like Earth could never have formed. You are made of their ashes. The atoms in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, were created inside stars that died before the sun was born. The ancient light of the CMB witnessed their formation, and now it surrounds you, the descendant of their legacy. The cosmic microwave background marks a wall, not a physical barrier. You couldn't crash into it or touch it, but an observational wall, a limit to what light can tell us. Before recombination, photons couldn't travel freely. The universe was opaque. Light was constantly scattered and absorbed, unable to carry information across space. So there is no older light to detect. The CMB is the edge of the visible universe, the oldest electromagnetic signal we can ever receive. Beyond it lies the epoch when the cosmos was a blinding fog. Beyond that lies the inflationary period, when the universe expanded faster than light in a fraction of a second. Beyond that lies the Big Bang itself, the moment when space and time as we understand them began. We can model these earlier periods. We can calculate what conditions must have been like. We can use physics to work backward and infer what happened, but we can never see it directly. The light from before recombination no longer exists in any coherent form. It has been absorbed and re-emitted so many times that its information is scrambled beyond recovery. The CMB is the boundary of seeing, the edge of cosmic vision. Everything older than 380,000 years after the Big Bang is hidden behind a wall of ancient fire, and we can only know it through mathematics and inference. This is humbling, and also, strangely, beautiful. To know that there is a limit to observation, to accept that some mysteries may remain forever beyond the reach of light. The patterns in the cosmic microwave background contain hidden information about the shape of space itself. And what they tell us is remarkable. By measuring the angular size of temperature fluctuations, how big the hot and cold spots appear on the sky, and comparing them to theoretical predictions, cosmologists made a startling discovery. The universe is flat, not curved like a sphere, where parallel lines eventually converge, not saddle-shaped like a hyperbolic surface, where parallel lines eventually diverge. Flat, Euclidean. The geometry you learned in school, where parallel lines stay parallel forever, where the angles of a triangle add up to exactly 180 degrees, applies to the universe as a whole. This might seem like a technical detail, but it has profound implications. The geometry of space determines the ultimate fate of the cosmos. A closed, spherical universe would eventually stop expanding and collapse back on itself. An open, hyperbolic universe would expand forever, becoming increasingly cold and empty. A flat universe sits exactly on the boundary between these possibilities, and flat is exactly what we observe. This is strange. There's no obvious reason why the universe should be flat. The conditions at the Big Bang could have produced any geometry. The fact that space is flat to such extraordinary precision suggests that something, perhaps inflation, fine-tuned the cosmos in its earliest moments. The ancient light told us the shape of reality, and reality, it turns out, is remarkably well balanced. The uniformity of the cosmic microwave background poses a problem, a deep, fundamental problem that puzzled cosmologists for decades. Look at one side of the sky. Measure the temperature of the CMB. Now look at the opposite side of the sky. Light that has traveled to you from a completely different direction, from a region of space billions of light years away from the first. Measure that temperature too. They match. To 1 part in 100,000. They match. This shouldn't happen. According to standard cosmology, those two regions of space were never in contact. Light hadn't had time to travel between them since the Big Bang. There was no way for them to exchange energy or information. They were causally disconnected, separated by distances so vast that nothing, not even light, could have bridged the gap. So how did they know to be the same temperature? How did opposite sides of the universe coordinate to have nearly identical conditions? This is called the horizon problem. And for years, it seemed like an impossible puzzle. The solution, most physicists now believe, is inflation. In the first fraction of a second after the Big Bang, somewhere around 10^36 seconds, the universe underwent a period of explosive expansion. Space itself stretched faster than light, growing from something smaller than an atom to something larger than the observable universe in an instant. Before inflation, the regions that would become opposite sides of the sky were close together. They were in contact. They had time to reach thermal equilibrium, to settle into the same temperature. Then, inflation blew them apart, stretching space so rapidly that they became separated by distances that seem impossible to cross. The uniformity of the CMB may be evidence that this cosmic inflation actually occurred. a fingerprint of the fastest expansion that ever happened, preserved in the ancient light. Before recombination, the universe rang like a bell. This is not a metaphor, not a poetic flourish. The early universe actually had sound waves, pressure waves rippling through the hot plasma, compressing and expanding the primordial matter in rhythmic oscillations. Think about what sound is. On Earth, sound is a pressure wave moving through air, regions of high pressure and low pressure, alternating, traveling through the medium. In the early universe, the medium was the plasma itself, a mixture of photons, electrons, and atomic nuclei, all tightly coupled together. When gravity pulled on a dense region trying to collapse it, the pressure of the radiation pushed back. The region would compress, then rebound, then compress again, oscillating like a spring. These oscillations sent pressure waves rippling outward, creating patterns of compression and rarefaction throughout the cosmos. These were sound waves in the truest sense. They had frequencies. They had wavelengths. If you could somehow have been there to hear them, the universe would have been humming with a deep, cosmic tone. Then recombination happened. The electrons and nuclei combined into neutral atoms. The photons were released. And suddenly, the sound waves had no medium to travel through. They stopped. They froze in place. The patterns they created, the regions of higher and lower density, were preserved in the temperature variations of the CMB. What we see when we look at the ancient light are the fossilized echoes of those primordial sounds, the frozen music of a universe that was once small enough to resonate. Here's something that shouldn't make sense. Something that troubled physicists for years before inflation provided an answer. The cosmic microwave background is almost exactly the same temperature in every direction. We've discussed this, but the problem is deeper than it first appears. Imagine 2 points on opposite sides of the sky. Light from one point has been traveling towards you for 13.8 billion years. Light from the other point has also been traveling towards you for 13.8 billion years. But those 2 points are not 13.8 billion light years apart from each other. They're more like 90 billion light years apart, because the universe has been expanding while the light traveled. This means that light from one side of the sky could never have reached the other side since the Big Bang. There hasn't been enough time. The two regions are outside each other's horizons. They are causally disconnected, unable to influence each other in any way, and yet their temperatures match to extraordinary precision. This is the horizon problem. It's like discovering that 2 people on opposite sides of the planet, who have never communicated and have no connection whatsoever, both happened to choose the exact same outfit this morning, down to the last detail. The odds are astronomical. The resolution, as we discussed, is likely inflation, but the problem itself illustrates something profound. The universe is stranger than our intuitions suggest, and the ancient light carries evidence of that strangeness, frozen into its patterns, for us to discover billions of years later. When you observe the cosmic microwave background, you are not seeing something that exists right now. You are seeing something that happened 13.8 billion years ago. Light that was released when the universe was only 380,000 years old. Light that has been traveling through expanding space ever since. In astronomy, looking far away is identical to looking back in time. This is because light travels at a finite speed. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at distant stars, you see them as they were years, decades, or centuries ago. The CMB takes this to an extreme. It is the ultimate time machine. When cosmologists study the ancient light, they are not studying a distant region of space. They are studying ancient time, frozen in radiation. The universe that emitted this light no longer exists. It has evolved, expanded, transformed into something completely different. Stars have formed and died. Galaxies have assembled and collided. Billions of years of cosmic history have unfolded. But the light itself remembers. It carries information from that ancient moment, preserved perfectly across nearly 14 billion years of travel. This is the only way we can directly observe the early universe. Not by traveling there, that's impossible, but by catching photons that were there, that witnessed those conditions firsthand, and have been journeying toward us ever since. The cosmic microwave background doesn't originate from a specific location. This is one of the most counterintuitive aspects of the ancient light, and it's worth taking a moment to truly understand. When astronomers observe the CMB, they detect it coming from every direction, not from a single point, not from a particular galaxy or region of space, from everywhere. It surrounds the Earth. Indeed, it surrounds every point in the universe, coming from all directions simultaneously. This happens because the CMB was released everywhere at once. At the moment of recombination, the entire universe became transparent simultaneously. Photons were freed from every location in the cosmos at the same moment, and those photons have been traveling ever since. Some toward us, some away from us, some in every possible direction. The photons we detect today are the ones that were released at just the right distance, 13.8 billion years ago, to be arriving here now. They come from a spherical shell around us, a surface of last scattering, located about 46 billion light years away in every direction. But here's the strange part. That shell isn't a place. It's a moment in time, frozen in light, and you are always at the center of it, because every observer is at the center of their own observable universe. The ancient light has been falling toward you from all sides for as long as the universe has existed. You're surrounded by the glow of creation, and you will never leave its embrace. Right now, as you lie still, the cosmic microwave background is passing through you. This is not a metaphor, not an exaggeration. Approximately 400 photons from the CMB occupy every cubic centimeter of space around you. They are drifting through your room, through your walls, through the earth, through everything. They pass through matter almost completely unhindered because they carry so little energy that they barely interact with anything at all. These photons are remnants of the primordial universe. Each one is nearly 13.8 billion years old. They were created in the hot plasma before recombination, released when the universe became transparent, and they have been traveling ever since. Patient, cold, utterly indifferent to whether anyone notices them. You are bathed in the oldest light there is. It doesn't warm you. It doesn't illuminate anything you can see. But it is there, always, everywhere. A silent presence, a constant companion, a reminder that you exist inside the fading afterglow of creation itself. In some sense, you have never left the light of the Big Bang. It has been surrounding you since the moment of your birth, since the moment of Earth's formation, since the moment the first stars ignited. It was here before humanity. It will be here after humanity is gone. It is perhaps the most constant thing in the entire universe, a gentle glow that has been present for almost all of cosmic history. For billions of years, the cosmic microwave background was here, filling the universe, saturating every corner of space, carrying encoded information about the beginning of time. And nobody knew. For the first billions of years, there was no one to know. Life had not yet emerged. Stars were forming. Planets were assembling. Chemistry was slowly building toward complexity. But there were no minds, no instruments, no curiosity. Then life appeared. Intelligence evolved. Humans looked up at the sky and wondered. But still, no one suspected that the entire universe was filled with ancient light, invisible and omnipresent. It wasn't until 1964 that two frustrated engineers, annoyed by a hiss they couldn't eliminate, stumbled upon the greatest accidental discovery in the history of cosmology. The cosmic background radiation had been there all along, passing through every human who ever lived, surrounding every civilization that ever flourished, filling the space between every star and galaxy. And we had no idea. It makes you wonder, how many other messages from the cosmos are we still missing? What other signals are passing through us right now, carrying information about the nature of reality, waiting for the right instrument or the right accident to reveal them? The universe is full of whispers. We have only just begun to learn how to listen. The cosmic microwave background is, in a profound sense, a message, a letter written in light sent 13.8 billion years ago, addressed to anyone in the universe patient enough to receive it. It tells us when the cosmos was born. It tells us what the early universe was made of. It tells us the geometry of space and the proportions of matter and energy. It tells us that the universe began hot and dense and has been expanding and cooling ever since. It tells us about inflation, about dark matter, about dark energy. It tells us about the first fluctuations that would become galaxies, and about the frozen sound waves that once rippled through the primordial plasma. All of this information has been traveling through space for nearly 14 billion years, encoded in patterns so subtle that they require the most sensitive instruments humanity has ever built to decode. But the message is there, and it has always been there, patient, waiting, carrying the story of the universe's birth across the vast emptiness of space. In some ways, the CMB is the universe's way of remembering its own origin, a self-portrait painted in ancient light, preserved across cosmic time. And now, finally, we have learned to read it. So what does it all mean? What does it mean to live inside this ancient glow, surrounded by photons that witnessed the birth of the cosmos? Perhaps it means that we are more connected to the universe than we usually realize. The same light that fills the space around you was present at the beginning of time. The atoms in your body were forged in stars. The fluctuations in the CMB became the galaxies that became the elements that became you. You are not separate from the cosmos. You are part of its unfolding story. Perhaps it means that the universe is patient beyond imagination. For nearly 14 billion years, the ancient light has been traveling, carrying its message, asking nothing in return. It doesn't care whether anyone receives it. It doesn't require acknowledgement or gratitude. It simply is, a constant, quiet presence, older than worlds, colder than anything you've ever known. Perhaps it means that there is beauty in the ancient and the vast. The CMB is not dramatic. It's not bright or colorful or attention-grabbing. It's a faint hum, a whisper at the edge of detection. And yet, it contains more information about the cosmos than almost any other source we can observe. The quietest things sometimes have the most to say, and so, as you lie here, surrounded by the oldest light in the universe, you might take a moment to consider the journey those photons have taken. They were released when the cosmos was still a glowing fog, 380,000 years after the Big Bang. They traveled through the dark ages when no stars shone. They witnessed the first stars ignite and the first galaxies form. They passed through billions of years of cosmic evolution, through the empty voids between galaxy clusters, through the vast expanses of nothingness that make up most of the universe. And finally, tonight, some of them are passing through you, through your room, through your body, through this moment. They have been waiting 13.8 billion years for this. Not specifically for you, the universe makes no such promises, but for any observer who might be here to notice. And tonight, you are that observer. So perhaps, as you drift towards sleep, you might offer a small, silent acknowledgement to the ancient light. Not because it needs acknowledgement, it doesn't, but because there is something meaningful in recognizing your connection to such vastness. You exist inside the afterglow of creation. You're made of materials that were once scattered across the cosmos by dying stars. The same forces that shaped the CMB shaped the galaxy that contains the sun, that warms the planet, that gave rise to the life that became you. History, cosmic history, stretches back nearly 14 billion years, and in all that time, across all that darkness, through all that patient traveling, the oldest light has never stopped. It is still here. It will be here long after humanity is gone. It will continue falling through space for billions of years more, fading slowly, stretching ever longer, until the universe grows so vast and cold that even this ancient whisper finally falls silent. But not tonight. Tonight, the ancient light is still here, still warm, barely, just 2.7 degrees above absolute zero, but still carrying the faint echo of the universe's first dawn, and you are here to sense it. So, settle deeper into your rest. Let your breathing slow. Let your thoughts dissolve like light fading into the distance. You are surrounded by something old and vast and quietly beautiful. A message from the beginning of time, delivered across billions of years, arriving in this room, in this moment, as you drift towards sleep. The universe has been sending this message for almost 14 billion years, and tonight, finally, you are listening. Let your eyes close. Let your body relax. Let the ancient light wash over you, unseen, unfelt, but present, as you drift into the darkness of rest. Good night, and thank you for spending this time wandering through the oldest light we can see. Let's return for a moment to that primordial darkness, to that era that astronomers call the cosmic dark ages, because there is something profoundly strange about that period that deserves our attention. Imagine this. The universe is only a few 100,000 years old. The light from the cosmic microwave background has just been released, traveling in all directions, but there is nothing to illuminate it. No stars, no galaxies, only hydrogen and helium gas, slowly cooling in the expanding expanse of space. If you could float in that primitive universe, you would see absolutely nothing. Not the familiar darkness of a moonless night, where you can at least make out silhouettes or hope your eyes adjust. No, total, complete darkness with no light source in any direction. The glow of the CMB would have already faded into the infrared, invisible to any eye that might have existed. This period lasted hundreds of millions of years, longer than complex life has existed on Earth, longer than dinosaurs dominated the planet. A cosmic silence so profound and so prolonged that it defies our understanding. And yet, something was happening. Something slow, something patient, something inevitable. Gravity was at work. In the slightly denser regions of the primordial gas, those tiny fluctuations we see frozen in the CMB, matter was beginning to accumulate, atom by atom, molecule by molecule. A process so gradual that it would take millions of years to notice any change. But time, in the universe, is not a scarce resource. The cosmos has infinite patience, and eventually, those small accumulations grew. They became denser. They attracted more matter from their surroundings, and the collapse accelerated. It's a bit like a snowball rolling downhill. At first, it barely moves. It picks up a few flakes. But as it grows, it picks up more, and more, and more, until what began as something insignificant becomes an unstoppable avalanche. Except this snowball was made of primordial hydrogen, and the hill was hundreds of millions of light years long. Now, let's shift to another aspect of this story, something you may not have considered. The cosmic microwave background doesn't just tell us what the universe was like, it tells us how we came to exist. Think of it this way. Fluctuations in the CMB, those tiny temperature variations of 1 part in 100,000, are the direct ancestors of everything you know. Every galaxy, every star, every planet, every atom in your body can trace its origin back to those tiny irregularities in the primordial plasma. If the early universe had been perfectly uniform, if the temperature and density had been exactly the same everywhere, no structure would ever have arisen. The gas would have expanded uniformly, cooling forever, with nothing interesting ever forming. An eternally empty, eternally boring cosmos. But it wasn't perfectly uniform. The quantum fluctuations of the first instant, vibrations in the very fabric of reality at incredibly small scales, were stretched by inflation into the seeds of cosmic structure, and those seeds, preserved in the ancient light, eventually blossomed into galaxies. When you look at the CMB map, you're looking at your cosmic family tree. The warmest patches are the regions that eventually became galaxy clusters. The coolest patches are the voids, the vast bubbles of nothingness that separate the structures of the universe. Somewhere on that map, there's a tiny fluctuation that eventually became the Milky Way. And inside that Milky Way, a small cloud of gas that became the sun. And around that sun, a disk of debris that became Earth. And on that Earth, eventually, you. It all begins with a small irregularity in the oldest light. Everything. There is something almost comforting about this connection. You are not an isolated accident in an indifferent cosmos. You are part of a chain of causality that stretches back to the very beginning of time. The same forces that created the fluctuations in the CMB created the conditions for your existence. You are literally made of patterns that formed in the earliest moments of the universe. Now, drift with me into something a little more technical. But don't worry, we'll keep it gentle. We've talked about how the CMB has a temperature of approximately 2.7 Kelvin, but there's something fascinating about how precise that number is. The exact temperature of the cosmic microwave background is 2.725 Kelvin, plus or minus 0.002 degrees. This measurement has been refined over decades using increasingly sensitive instruments, and we now know it with extraordinary precision. But here's the interesting part. That temperature isn't constant over time. It's decreasing. As the universe expands, the CMB cools. Not rapidly, in fact, so slowly that it would take billions of years to notice a significant change, but steadily. When the universe was half its current age, the CMB was about twice as hot. When it was 1/10 its current age, it was about 10 times hotter. If you could travel back in time, you would see the temperature of the CMB rise. The universe would become warmer, denser, and brighter. Eventually, you would reach a point where the CMB would no longer be microwaves. It would be visible light. And before that, it would be ultraviolet light. And before that, X-rays. And before that, the blazing plasma of the early universe. The temperature of the CMB is like a cosmic thermometer. It tells us not only how much the universe has cooled, but also how much it has expanded. Each degree of cooling represents eons of cosmic expansion. And in the distant future, the very, very distant future, the CMB will continue to cool. Eventually, it will reach temperatures so close to absolute zero that it will be almost impossible to detect. Photons will stretch to wavelengths longer than entire galaxies. The echo of the Big Bang will fade to a whisper so faint that even the most sensitive instruments imaginable would struggle to pick it up. But that's trillions of years in the future. For now, the ancient glow is still here, still detectable, still telling its story to anyone with the patience to listen. Let's now move on to something that might surprise you. Something that has to do with your own position in the cosmos. When scientists precisely map the cosmic microwave background, they notice something peculiar. There's a slight asymmetry. One direction in the sky is slightly warmer than the opposite direction. Not by much, just a few thousandths of a degree, but consistently. The reason? We're on the move. The Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way moves through local space. And the entire local group of galaxies is falling toward a huge concentration of mass called the Great Attractor. When you add up all these movements, it turns out we're traveling through the universe at approximately 600 kilometers per second. That's over 2 million kilometers per hour. Fast in human terms, insignificant in cosmic terms. This movement creates a Doppler effect in the CMB light. Light coming from the direction we are moving is slightly compressed, shifted toward shorter wavelengths, which means higher temperatures. Light coming from the opposite direction is slightly stretched, shifted toward longer wavelengths, lower temperatures. Scientists call this the CMB dipole. And once they correct for it, once they mathematically subtract our own motion, they can see the true primordial fluctuations underneath. It's curious to think about. The ancient light that fills space carries a tiny imprint of our movement. We can measure our speed through the cosmos simply by observing how the CMB appears slightly warmer in one direction than another. It's as if the universe had a cosmic speed radar, and we were receiving our speeding ticket in real time. There's another mystery hidden in the cosmic microwave background, one that scientists haven't fully solved yet. It's called the cold spot. In the southern hemisphere of the CMB sky, there is a region that is abnormally cold, not dramatically cold. We're talking about a difference of approximately 70 microkelvins, 1/70 millionth of a degree, but significantly colder than statistical models predict. Scientists have proposed several explanations. Perhaps it's simply a statistical fluctuation. The universe is large, and on a map with so many points, you would expect some outliers. Perhaps it's a super void, an unusually empty region of space that cooled the CMB light as it passed through it. Perhaps it's something more exotic. Some have even speculated that it could be evidence of contact with another universe in a multiverse. The truth is, we don't know for sure. The cold spot remains one of the little mysteries of the cosmos, a reminder that even after decades of study, ancient light still holds secrets we haven't yet unlocked. It's comforting, in a way, to know that there are still unanswered questions, that the universe hasn't revealed all its secrets, that there will always be something more to discover, something more to wonder about, something more to keep human curiosity alive. Although perhaps not tonight. Tonight is for resting. Now, let's float towards something more contemplative. Sometimes, when I think about the cosmic microwave background, I wonder what it would mean to someone living in the very distant future. Today, the CMB is relatively easy to detect. It fills the sky with a clear, uniform signal. Any civilization with moderately advanced radio technology should be able to find it. But the universe is expanding, and as it expands, the CMB cools and stretches. In billions of years, it will be harder to detect. In trillions of years, it will be nearly impossible. And there's more. As the universe ages, distant galaxies are moving away from us faster and faster. Eventually, due to the accelerated expansion driven by dark energy, the most distant galaxies will disappear completely from view. They will cross the cosmological horizon, the point beyond which light will never be able to reach us, no matter how long we wait. A civilization that arose in that distant future would look to the sky and see almost nothing. Its own galaxy, perhaps a few nearby galaxies that remained gravitationally bound, but nothing more. No evidence of the Big Bang, no detectable CMB, no way of knowing that the universe was once filled with trillions of galaxies, all moving away from each other. They would believe that their galaxy was all that exists, a solitary island of stars in an infinite ocean of emptiness. It's a melancholic thought. Those future civilizations would never know the true history of the cosmos. They would never receive the message that the ancient light has been sending for billions of years. They would have arrived too late to hear it. But not us. We are here now, in this cosmic window of time, perhaps a relatively brief window on the grand scale of things, where we can still see evidence of the beginning, where the ancient light is still detectable, where the message is still being delivered. There's something precious about that. Something we should perhaps appreciate more than we do. Let me tell you about something called the surface of last scattering. When the CMB photons were released during recombination, they didn't come from a single point. They came from everywhere, simultaneously. The entire universe became transparent at the same time, and photons were released from every location in the cosmos. The photons we detect today are those that were released at precisely the right distance to be arriving here now. Imagine a giant sphere centered on the Earth. On the surface of that sphere, 13.8 billion years ago, photons were released that are now reaching our detectors. That sphere is called the surface of last scattering. It is the place, or more precisely, the moment, where light and matter were last separated, where photons were last scattered before traveling freely through space. But here's the strange thing. That surface isn't 13.8 billion light years away. It's approximately 46 billion light years away. How can that be? How can something be farther than light could have traveled in the age of the universe? The answer is the expansion of space. As the light traveled toward us, space itself was stretching. The distance between us and the source of the photons increased even as the photons moved closer. It's like walking forward on a treadmill that's lengthening. You may be moving toward your destination, but the destination is also moving away. The result is that the surface of last scattering is now incredibly far away, farther than light could reach if it started traveling today. It is beyond what we call the cosmic event horizon. And that means we can never go back to it. We can never visit it. We can only observe it through the light that has been traveling ever since. A light that tells the story of a place that is now irrevocably beyond our reach. There's a certain poetry to that. Being surrounded by the light of places we can never go. Receiving messages from a distance that grows faster than any journey could ever overcome. Part 4. Now delve with me into something a little more intimate. Something about the experience of living within this ancient light. Right now, as you hear these words, approximately 400 photons from the cosmic microwave background are passing through every cubic centimeter of your body. You don't feel them. You don't see them. But they are there. These photons are incredibly old, almost as old as the universe itself. They have been traveling for 13.8 billion years, traversing distances so vast they defy comprehension. And now, at this very moment, they are passing through you. It's a form of contact with the cosmic past, not metaphorical, but literal. Particles that existed before stars ignited, before galaxies formed, before anything you would recognize as normal matter existed. Those particles are interacting with you right now. Of course, the interaction is minimal. CMB photons have so little energy that they pass through matter with almost no effect. They don't heat you up. They don't illuminate you. They don't do anything you can directly perceive. But still, the connection is there. It exists. It's real. You are bathing in the light of the beginning of time. You have been doing this your entire life. You will be doing it until the moment of your death. It is one of the few absolute constants of human existence. More constant than the weather. More constant than the seasons. More constant than anything else in your environment. The ancient light has always been here, and it always will be, at least for as long as humanity exists. There's something scientists have discovered about the cosmic microwave background that's rarely discussed outside academic circles. It has to do with polarization. Light, as you probably know, is an electromagnetic wave, and as a wave, it has a property called polarization, the direction in which it oscillates as it travels. Normally, when we look at the stars or the sun, the light we receive is randomly polarized. The waves oscillate equally in all directions. But the CMB is not randomly polarized. It has very specific polarization patterns, and those patterns contain additional information about the early universe. There are two main types of polarization in the CMB. Scientists call them E modes and B modes. E modes are simpler patterns, created by the same density fluctuations that produce temperature variations. B modes are more complex, and this is where things get really interesting. Some B modes are created when CMB light is deflected by the gravity of matter between us and the surface of last scattering, an effect called gravitational lensing. But scientists believe there could also be primordial B modes, patterns created by gravitational waves generated during inflation in the first fraction of a second after the Big Bang. If we could detect these primordial B modes, we would have direct evidence of inflation. We would have a window into the earliest moments of the cosmos, even before the CMB was released. It would be like finding a recording of the sound of the universe being born. Several experiments are searching for this signal. So far, it has proven elusive. But the search continues, and the ancient light still guards its secrets, patiently waiting for us to develop the technology to decipher them. Let's go back to something simpler, something closer to human experience. The cosmic microwave background has a peak frequency of approximately 160 GHz. That means the most common wavelength of its photons is approximately 2 millimeters. Do you know what else operates on similar frequencies? Your microwave oven. A typical microwave oven operates at 2.45 GHz, significantly lower than the peak of the CMB, but in the same general range of the electromagnetic spectrum. Both are microwaves. Both are forms of electromagnetic radiation too long to see, too short to be picked up by an ordinary radio antenna. There's something slightly absurd about this. The same type of radiation you use to reheat dinner leftovers is the same type of radiation that fills the entire universe, carrying the echo of the Big Bang. The next time you use a microwave, you might reflect on the fact that you're harnessing the same kind of energy that has been traveling through the cosmos for nearly 14 billion years. Sure, the photons in your microwave are much more energetic. They're designed to stir up water molecules and generate heat. The photons in the CMB are too weak to do anything similar, but they're related. Distant cousins, if you will. It's comforting, in a strange way. Even the most mundane kitchen technology has connections to the deepest mysteries of the cosmos. Now, let me guide you through something you may never have considered. The cosmic microwave background is not uniform in time, only in space. When I say the CMB has the same temperature in all directions, I mean that if you point your detector north, south, east, or west, you get roughly the same result. The spatial uniformity is extraordinary. But temporarily, things are different. The WBC we receive today is not exactly the same as the WBC we received yesterday, nor the one we will receive tomorrow. Why? Because the photons arriving today were emitted from a slightly different sphere than the photons that arrived yesterday. The surface of last scattering is an expanding sphere. Each day, we are receiving light from a slightly older and slightly more distant layer of the early universe. The differences are minuscule, imperceptible with any current technology, but they exist in principle. Every moment, we are seeing a slightly different slice of the cosmic past. It's as if the universe were projecting a film, frame by frame, at such a slow speed that it appears as a still image. But if you could speed up time, if you could condense billions of years into seconds, you would see the image change. The patterns of the CMB would slowly evolve as we observe ever deeper layers of the past. Of course, we don't have billions of years to wait, and the differences between one day and the next are so small we can't even measure them. But there's something contemplative about the idea. The message we're receiving isn't static. It's changing, imperceptibly, moment by moment. The ancient light still has more to tell. We just need cosmic patience to hear it. There's a question that sometimes keeps me up at night. Not from anxiety, but from wonder. What was the light doing before it was released? For the first 380,000 years of the universe, photons existed, but they couldn't travel. They were trapped in a constant dance with matter, absorbed, re-emitted, scattered, absorbed again. Each individual photon bounced from particle to particle, unable to escape, unable to carry information from one place to another. It was a kind of prison, a jail of fire and density, where light existed but could not fulfill its purpose. The photons were there, carrying energy, but completely incapable of illuminating anything. And then, suddenly, freedom. The universe cooled enough for electrons to bind to nuclei. Suddenly, there was nothing to bounce off of. Photons, after hundreds of thousands of years of confinement, were released simultaneously throughout the cosmos. It must have been the greatest prison break in the history of the universe. Trillions upon trillions upon trillions of photons, all released at the same moment, all beginning their billion-year journey through the void. And now those same photons are arriving here, to this planet, to this room, to you. The journey they began 13.8 billion years ago is finally coming to an end, at least for some of them. Those who reach you tonight have completed their odyssey. They have traveled farther than anything you could possibly imagine, for longer than anything you could possibly conceive. And its final destination, after all that, turns out to be you. It's probably not what they expected, if photons could expect anything. They probably imagined ending up in a star, or a galaxy, or something more dramatic. Not a human lying in a bed, listening to a story about them. But here we are. End of the journey. Thank you for having us. Let's talk a little bit about what the CMB tells us about dark matter. Dark matter is one of the most mysterious substances in the universe. It doesn't emit light. It doesn't absorb light. It doesn't interact with light in any way we can detect. The only reason we know it exists is because of its gravitational effects. Galaxies rotate too fast. Galaxy clusters are too massive. The universe has more structure than it should if only normal matter existed. But here's the fascinating part. The cosmic microwave background provides independent evidence for dark matter. And not only that, it allows us to measure exactly how much of it exists. The patterns in the CMB, the temperature fluctuations, the angular sizes of the hot and cold spots, depend on the composition of the early universe. The amount of normal matter affects these patterns in one way. The amount of dark matter affects them in a different way. When scientists analyze the CMB data with sufficient precision, they can disentangle these contributions. They can say, to produce exactly these patterns, you need this amount of normal matter, this amount of dark matter, and this amount of dark energy. The results are remarkable. The CMB tells us that dark matter outweighs normal matter by approximately 5-to-1. For every atom of hydrogen or helium or any other element you know, there is roughly 5 times as much mass in the form of dark matter, a substance we have never seen, never touched, and are only just beginning to understand. Ancient light, it turns out, not only tells us the story of the visible universe, it also reveals the presence of the invisible. The CMB is a map not only of the matter we can see, but also of the matter we cannot. And speaking of invisible things, let's consider dark energy. Dark energy is perhaps the deepest mystery of modern cosmology. It is a force, or a property of space itself, that is causing the expansion of the universe to accelerate. Before its discovery in 1998, scientists assumed that the expansion of the universe was slowing down, held back by the gravity of all the matter it contains. But observations of distant supernovae revealed the opposite. The universe is expanding ever faster. The cosmic microwave background confirms this picture. Patterns in the CMB combined with other observations, indicate that approximately 68% of the total content of the universe is dark energy. Not matter, not radiation, a form of energy that permeates empty space and pushes against gravity. No one knows what dark energy is. It could be a fundamental property of space-time. It could be a quantum field we haven't yet identified. It could be something else entirely, something that requires new physics to explain. But we know it exists, and we know how much there is. And we know this, in part, because the ancient light told us so. When you add it all up, normal matter, dark energy, you get a picture of the cosmos that is profoundly humbling. The 5% of normal matter includes everything you can see, touch, or directly interact with. Stars, planets, people, atoms, everything. The other 95% is mystery. Dark, invisible, incomprehensible for now, and yet completely real. The universe is mostly things we don't understand, and the ancient light patiently reminds us of that every time we study it. There's something else I want to tell you about: the cosmic microwave background. Something about silence. The CMB is incredibly uniform. We've discussed that. The fluctuations are on the order of 1 part in 100,000. Barely ripples on an almost perfectly smooth surface. But think about what that means. Before recombination, the universe was a turbulent plasma. Pressure waves rippled through it. Regions compressed and expanded. There was movement, chaos, activity. And then suddenly, everything stopped. The plasma turned into neutral gas. The pressure waves had nothing left to compress. The sound, because that's what they were, sound waves in a cosmic medium, simply ceased. The universe, at that moment, became silent. For hundreds of millions of years after that, the silence continued. No stars to shine, no galaxies to spin, nothing but gas cooling in the darkness. The cosmic microwave background is the last sound before the great silence, the final echo of an age of chaos, frozen in light just as stillness was beginning. And now that echo reaches us, piercing the silence, bringing us news of a time when the universe still sang. It's time to start wrapping up this journey. Tonight, you have traveled farther than any spacecraft ever will. You have journeyed back in time farther than any time machine could take you. You have gazed upon the oldest light in the universe, photons that were released when the cosmos was just a baby, that have been traveling for nearly 14 billion years, and that have now, finally, found you. The cosmic microwave background is many things. It is evidence of the Big Bang. It is a map of the early universe. It is a tool for measuring the composition of the cosmos. It is confirmation of theories that seemed too strange to be true. But it's also something simpler. It's a message sent nearly 14 billion years ago, addressed to any being in any corner of the universe who might have the technology and the curiosity to receive it. It wasn't sent intentionally, of course. The universe has no intentions, but the message is there nonetheless. A letter from creation, delivered across the void, patiently waiting to be read. And tonight, you have read it, or at least you have listened as someone told you its contents. You have received news from the beginning of time. You have contemplated your connection to the primordial cosmos. You have remembered that the atoms in your body were forged in stars, born from fluctuations that are still visible in the ancient light. That's something. That's something real and meaningful. The universe is vast and mostly empty. Time is long and mostly silent. But here, in this tiny moment, in this small room, on this small planet, you exist. And you exist connected to everything else through the light that has been traveling towards you from the very beginning. So tonight, as you settle deeper into your rest, surrounded by running water, steady light, and quiet walls, perhaps you can pause for a moment. Perhaps you can offer a small, silent thanks to the light that surrounds you, so ancient, so patient, so utterly indifferent to whether anyone notices it, because history, like the universe, can be vast, uncomfortable, and quietly intimidating. But it is also proof that across centuries and across stars, beings persist, curious, resilient, and a little absurd. The photons from the cosmic microwave background will continue to pass through you while you sleep. They will continue to fill the space around you. They will continue to carry their ancient message, regardless of whether anyone is awake to receive it. They've been doing this for billions of years. They'll do it for billions more years. And you, for a brief moment on the grand cosmic scale, are here to witness it. Let your eyes close. Let your body relax. Let the ancient light envelop you, invisible, intangible, yet present, as you drift into the darkness of rest. The universe has been sending its message for almost 14 billion years. And tonight, finally, you are listening. Good night. And thank you for spending this time wandering through the oldest light we can see.